Okay, let's look at example for irrational roots and the coefficients of a polynomial. How are the types of zeros of a polynomial function related to the coefficients of the polynomial? Part A. Suppose a quadratic polynomial function p has one rational zero c and one irrational zero a plus root b, where a and b are rational numbers. Are all the coefficients of p rational? How can we answer this question? Well, what do you know about the product of a rational and an irrational number? The product of a rational and irrational number is always irrational, because if you have an irrational number, then if you multiply, that irrational number is not going to go away. Irrational numbers can only be rational when it's irrational times irrational, right? So rational and irrational will make a product of irrational. So there should be at least one irrational coefficient when you multiply rational and irrational coefficients. Okay, but a and b are rationals, but we don't know if root b is going to be rational or not, depending on what it actually is. So not all coefficients of p are rational, right? How can we prove this? You can write this in terms of its factors. So factor out x minus c times x minus a plus root b, and then you can see if you can multiply them, right? So yeah, it has one rational zero c, so you can write it as a factored form first, and then multiply it to get your polynomial, and look at the coefficients. So your a, b, and c should represent your coefficients, actual numbers, right? So the first time, no problem. A plus root b plus c, that is irrational. And then a plus root b, that's also irrational. So you have two irrational coefficients. It's not going to be rational. It's not all coefficients are going to be rational. Okay. So there's a lot of imagining for you if you're not really comfortable with rational and irrational, and if they're closed or open in operations. So I recommend getting comfortable with the operations of rational and irrational numbers. Not just computation wise, but also like their nature wise, their concept wise. Like, are we always going to get irrational? Are we always going to get rational? All right, part B. Suppose a quadratic polynomial function R has two irrational zeros. A conjugate pair, so remember your vocabulary, conjugate is when you have the second term with the different sign, but you basically have the same terms. So a plus root b and a minus root b, where a and b are rational numbers, are all the coefficients of R rational. Well, you can write them as two factors and then multiply and see if they are rational. So if you multiply, simplify, these are your constant, and these are your coefficients. 2a, if a is rational, 2a is rational. And then a squared, that should be rational, because rational times rational square should be rational. And then minus b, which is also rational, that should be rational minus rational, so that's rational. So 2a rational, 1 rational, 2a squared minus b rational. They're all rational numbers. So yes, R has only rational coefficients. So what can we say? A quadratic function with one rational zero and one irrational zero, where a plus root b, where a and b are rational, will have some irrational coefficients. But quadratic with conjugate pairs of irrational zeros will have only rational coefficients. So unless it's conjugates, it is always going to have rational coefficients. This is nice to know because you know what to expect. Okay, let's look at try number 4. Suppose a quadratic polynomial function f has two complex zeros, which are a conjugate pair, a minus bi and a plus bi, where a and b are real numbers. Are all the coefficients of f real? Explain. So pause the video, think about it for a minute, and see if you can answer this with your own words, with your own reasoning, with your own logical steps like this. Okay, come back when you're ready for answers. Okay, are you ready? So remember, they are a conjugate pair, a minus bi and a plus bi, where a and b are real numbers. Okay, it has two complex zeros. Are all the coefficients of f real? It's very similar to part B, right? We already expect, oh, if it's going to be conjugates, then it's going to cancel each other out, and then it's going to be rational. And you're right. Let's look at the work. So I'm going to put the work here. So f of x is could be written as x minus a minus bi. That's one complex number. And then another one, x minus a plus bi. That's the conjugate. Okay, and then you're going to multiply. You're going to, let's use the associative property and say, oh, we can group x minus a together, and then plus bi for this factor. And then same thing for here. We can group x minus a here, and then minus bi here. And then you can factor out, because x minus a is the same and then bi is the same. So you can factor out x minus a square and then bi square. Difference of squares. And then you can multiply them and then simplify. X squared minus 2ax plus a square plus b square would be your last polynomial. And now look at your coefficients. Negative 2a, rational. A squared, rational. B squared, rational. They are all real. Are all the coefficients of f real? Yes. They are not imaginary numbers. So, yes. Okay. Good. So let's talk about conjugate root theorems as a concept. Let p be a polynomial function with rational coefficients, and let a and b be real numbers. Then, if a plus root b is a root of p of x equals 0, then a minus root b is also a root of p of x equals 0. So we just figured that out looking at example 4. Let p be a polynomial function with real coefficients, and let a and b be real numbers. Then, if a plus bi is a root of p of x equals 0, then a minus bi, which is the conjugate, is also a root of p of x equals 0. So we should know that the conjugate roots are also going together. They go together because if it's rational, you need to have conjugates for imaginary number. All right. Very important, because now if you figure out one root for the imaginary, for a complex root, then you know that the other conjugate pair is going to be one of the roots as well. Let's continue with example 5 in the next video.